Hi, we are now in position to present the connection of the stochastic derivation that we did in the previous video with the two derivations that we have so far presented. So let's do that. In the stochastic derivation, we have found that the stochastic velocity, which we represented by u, was written in terms of the logarithm of a function r. Note that we have represented it by 2 times d0 ln of r, but d0 was written as h over 2m. Since r can be 0 sometimes, it's better to write this in terms of r squared divided by 2m, so that we get, since r is a real function, the logarithm of a real function. Okay? Of course, when r goes to 0, we'll have here some singularities. So we can express the stochastic velocity in these terms, and this, of course, is just S, our entropy, divided by Boltzmann constant. These expressions allow us to write the divergence of the stochastic velocity in these terms, but we have already found this term in our entropy derivation. So the stochastic velocity is connected to fluctuations, because we have found exactly this value for fluctuations in the entropy derivation, saying that the fluctuation over momentum in each point of the configuration space is related to the divergence of the stochastic velocity. By making such a connection, we now mathematically show that our fluctuations are related to stochastic behavior. This connection can be developed even further if we remember that we can write our characteristic function z, q delta q time, as whole q plus delta q time. This is plus or minus, doesn't matter. This was done in the entropy derivation, and this allowed us to write the characteristic function in these terms. At that point, we have shown that this is related with our stochastic momentum, and this one was also related to stochastic behavior. This is what we now learn from the connections between the two derivations. Okay, we now can profit from this connection between these derivations. We can, of course, express the stochastic velocity in usual terms found in statistical mechanics books. We always find the stochastic velocity connected by some coefficients to the derivative of the entropy, so this is not an unexpected result. And this coefficient here is connected to this expression. Our assumption is that these coefficients are different from 0 only when we take I equal to j, and they are equal. They are our d0. And of course, d0 was found to be this value. But this expression has a deep consequence, in fact, deep consequences on our interpretation of quantum mechanics, as we will show in the videos to follow. In fact, this is a version, the mathematical version of the fluctuation dissipation theorem, and we know that this fluctuation dissipation theorem is connected to Langevin equations. In fact, we will show as our last derivation, the sixth derivation, that we may find the Langevin equations for quantum mechanics, showing unequivocally that quantum mechanics has stochastic support. But the main gain that we have with these derivations and connections, mathematical connections, is the fact that we are now in position to interpret some results of quantum mechanics using not only the notion of fluctuations, but also the notion of stochastic behavior. For instance, one of the interpretation results that we will have is the possibility of connecting ensemble average to time averages. And this will help us show that quantum mechanics has to apply both to ensemble and to single systems. This will be what we will do in the next video. We can finally connect the two approaches by showing that our general velocity, as defined in the stochastic derivation, can be connected to a systematic velocity, which is just gradient of s over m, our p, and the stochastic velocity, which is just gradient of s, proportional to gradient of s. So this is the expression of the connection between the two approaches. Okay, in the next video I will show how to use all these results to show that we may connect ensemble and single systems interpretations using the notion of the ergodic principle that now I can talk about because I am in the realm of stochastic theory. This is what I must stress here. This is what we gain when we connect a number of different derivations of the Schrödinger equation. We get other symbols of the theory. For instance, now we have stochastic velocity, but we have these symbols entering the theory in a controlled way, since we are controlling the way quantum mechanics is obtained by deriving the Schrödinger equation and connecting these derivations all together. So thank you for watching. See you in the next video.